Welcome back, everybody. So in previous work in this integration section, we have absolutely seen the ubiquity of expressions, like, for example, the supremum of a set minus the infimum of a set, or its more complicated version where we look at, say, the upper sum of a partition minus the lower sum of a partition. So this is special enough, and we've used it enough. I want to give it a special name, and this is not a standard name for it, but I think this is a reasonable name for it. So let's start with a definition then. So I'm going to start with a bounded function from a closed interval AB. And so first, if I is some subset, so very often this will be an interval, but let's just say it's some subset of AB, then the F spread. Okay, so the F spread of I is, okay, so the notation we'll use is SPR F of I. So this will be the F spread of I. And this is simply going to be the supremum of F on I minus the infimum of F on I. All right, so that we've already used a little bit, but now we'll have a nice short name for it. As we do integration, we're very often going to actually want to apply this when we have a partition. So if I have a partition W of the interval AB, well then again the F spread, but now it'll be for the partition. So the F spread of W is, well, I'll use the same notation here, only now I'll evaluate it on the partition. And instead of doing just this, like the supremum of F on, well, I don't know what I would do it on, I actually know I can break up W, right? W0, W1, and so forth, right? And I have my intervals, IK, which is WK minus 1 to WK. And of course, I can look at these sums, right? I look at the supremum, for example, of F on each IK. And then I multiply by the length of IK. And what is that? Well, that's the upper sum. But I could also then subtract the lower sum. And if I do, I'll get this infimum of F on IK rather, times the length of IK. Fine. And of course, I can put these together as one sum. I factor out the length, and I'll end up with the supremum of F on each IK minus the infimum of F on each IK. So it makes sense then to refer to the spread of the entire partition as the difference of the upper sum on W minus the lower sum on W. Okay, it's not an exact analogous thing because we're actually adding in these lengths and everything, but it's pretty good. It's pretty good here. Well, maybe one more little bonus definition. So, of course, I could be looking at all of the partitions. So let's say I take P and define that to be all the partitions on AB. Then I could actually even talk about the F spread of P, and this would simply be the set of all F spreads on all partitions. Right, so that will that'll come into play in our theorem. So the nice thing is that we have all of these results that tell us how to handle properties of suprema, infima, upper sums, and lower sums. And so a lot of those are just going to port over to the F spread. So that's going to be the next thing we do here, build a little theorem, and this is just going to be spread properties. Okay, so as we've had in the past, I'll take two functions now from A, B to R, we'll assume both of them are bounded. We'll let C be some real number. And then let me take a couple of partitions of AB. Okay, and I'm going to use this same notation here for W. Okay, so I'll just port that notation down here. So the first result is that if, well, we already defined W here. I'll just say the spread, the F spread of W, I can write this now as the F spread of each IK times the length of IK. Okay, and I'm going to take the sum. So this is showing you the connection here between the spread of a partition and the spread of an interval. Okay, so this is handy. It's not, of course, hard to prove. It really just comes right from these definitions. Okay, so when I do the upper sum minus the lower sum, I end up with the supremum minus the infimum. That's precisely the F spread, right? The F spread on IK. So nothing terribly deep here, right? This is just the definition. All right, the second thing, if I know that X has W as a refinement, so W refines X, then the spread, the F spread of W, will be less than or equal to the F spread of X. Okay, so refining your partition will make the spread smaller. And we've actually used this before. We didn't call it spread in the past, but that's what happens. So let's just do a little proof here. We'll just toss it in. So this basically comes because, okay, the F spread of W we know is equal to the difference of the upper sum minus the lower sum. But we know when you get a refinement, the upper sum has actually gotten smaller. So if I replace the upper sum of W with the upper sum of X, I'm getting bigger. And when I refine, the lower sum actually gets bigger. So if I replace the lower sum of W with the lower sum of X, well, actually I'm getting a smaller lower sum. And so the difference between the upper and the lower has gotten bigger when I do the refinement. Okay, so if this is all seeming very strange to you, you got to remember we had this result that if I take the lower sum of X, that will be less than or equal to the lower sum of a refinement, which is always, of course, less than or equal to the upper sum, which is less than or equal to the upper sum of the refined partition, right? The original one. So the outer bit is obviously going to be at least as big as the inner bit. And since this last one here is the F spread, the result is proved. Okay, so you can see up here in our picture, right, here is your F spread of X, and down here you have your F spread of W. So when we refine, our spreads get smaller. Okay, the next statement, number 3. If I look at the F plus G spread of W, so remember I have two functions, F and G, which are both bounded, so I can compute this F plus G spread. This is going to be less than or equal to the F spread plus the G spread. All right, and once again, this is going to come from our properties of upper sums and lower sums. So we can write down a proof of this pretty easily. Oops, let's get that back to green there. Okay, so if I take the lower sum of W plus the lower sum, of course, is the F lower sum, and then I take the G lower sum for W. This is less than or equal to the F plus G lower sum of W. So this goes back to the previous video where we show that, okay, the lower sum of F plus G is at least as big as the sum of the lower sums for F and G. So I'm just writing that backward here. Okay, this lower sum less than or equal to the F plus G lower sum. Of course, every lower sum is less than or equal to every upper sum. But now the upper F plus G sum, right, that is less than or equal to the sum of the F upper sum and the G upper sum. Okay, so we now have this chain of equalities. So what does that tell us about the spread? Well, if I start subtracting, all right, so here I have this subtraction in the middle, UF plus G minus LF plus G. This difference is going to be the F plus G spread. Okay, but if I subtract this top piece from the bottom piece here, well, now I have UF minus LF, and I have UG minus LG. That's precisely the sum of the F spread and the G spread. Okay, and so that shows that the F plus G spread is bounded from above by the sum of the F and G spreads. Okay, so that proves 3. Okay, what's number 4? Well, if you've been paying attention, after we look at what happens to F plus G, we're going to look at what happens when we multiply F by a constant. All right. Now, in the previous couple videos, every time we multiplied by some constant, our answer depended ultimately on whether the constant was negative or positive. What's kind of cool here is it's not going to matter as much in this case. So if I take the CF spread of W, this is going to be the absolute value of C times the F spread of W. So I don't need to write down this in sort of 2 different ways here. I always, no matter whether C is positive or negative, I actually will get the same value. Okay, and this is maybe a little surprising, and then as we work through it, you'll see why it's just what has to happen. Okay, so we know that the CF spread, so the CF spread of W, okay, well this is the CF upper sum minus the CF lower sum. All right, now if C is greater than or equal to 0, then our properties for upper and lower sums, okay, so we knew that when C was greater than or equal to 0, you could just pull the constant out. When you had UCF, you just make it CUF. So I can make this CUF of W. And similarly with the lower sum, we got to pull the C out. So this is when C is greater than or equal to 0. If C is negative, well, let's see what happened when C was negative. We could pull the C out, but the upper turned into a lower sum. And if we scroll down, we'll see with 4, the same thing happens, only lowers turn into uppers. So in this case, we pull the C out of the upper, it becomes a lower. And we pull the C out of a lower, it becomes an upper. All right, so that's when C is negative. All right, well, in the first case, I have C times upper minus lower. That's just the F spread. Which, of course, I could write as the absolute value of C. That doesn't hurt anything. So that's when C is greater than or equal to 0. And here I can pull the C out, and I get, well, let's see, lower minus upper. That's the negative of the F spread. Well, let me just put the negative at the front, And then I'll have negative c times the f spread. But when c is negative, negative c is the absolute value. So this is again equal to the absolute value of c times the f spread of w. So in either case, we get the absolute value of c times the f spread. Okay, so that finishes the proof of number 4. All right, number 5. And this really is mostly for convenience. It's nothing really new here. F is integrable if and only if. Can we write this in terms of the spread? Well, we have the integrability criterion. And the integrability criterion would tell us that f is integrable if and only if we can get the difference between the upper and lower sums less than epsilon, or maybe some positive constant times epsilon, but that doesn't matter so much. All right, but if we're getting the upper minus the lower, we're talking about the spread being less than epsilon, right? For any epsilon. Okay, but if we can do it for any epsilon, then we can really shorten this up and just say, if I take the infimum of the f spread across all partitions, then this would equal 0. Okay, so this just follows immediately from the integrability criterion. This is nothing new, just a rephrasing in terms of this notation. Okay, number 6. Oops, want that in black. Number 6. So in number 6, this is actually, we're going to build up 3 different statements, 6, 7, and 8, that are all sort of interlinked, but independently interesting. So again, if I have some, say, subset I of this interval AB, then another way that we can write down the f spread of I is by looking at the supremum of all differences of the form f of x minus f of y, where x and y are elements of I. So somehow the spread is just measuring how far apart the biggest stuff of f is from the smallest stuff, right? In the range of f. So let's try to prove that. So this won't be too bad. So we want to use the sup and inf omnibus theorem. Okay, so the two things that we knew, one is that if I had the supremum of a sum of sets, it was the sum of the suprema. So that was one thing. The other was that if I had a constant, I could pull the constant out, and if that constant was negative, then I would replace the supremum with an infimum. So we're going to use both of those in this proof. So let's see here. So let's start with actually the right-hand side. So I have the supremum of all possible differences, f differences of elements from I. And I can rewrite this as the supremum of, well, okay, so I'm going to take f of something in I, and I'm going to do that for all possible x. So I could just look at this as the range of f. And then, well, what do I add to it? Okay, well, this has a minus, but I can turn that into a plus. The negative of f of I. So I'm taking everything in I. I'm evaluating f on it. That gives me f of I, but I stick a negative in front. I look at all those sums. I take the supremum. But now I have a supremum of a sum of sets. And so I can break this up as the supremum of f of I plus the supremum of negative f of I. And now I'd like to pull this negative out, but because, well, a negative is a negative, this supremum will have to turn into an infimum. So this will be the supremum of f of I minus the infimum of f of I. Oh, but this is precisely the f spread of I. Okay, so there we go. We have proved the result. Okay, so let's move on to number 7. So in number 7, back to black. There we go. Number 7, I'm going to keep this same I. And now I'm going to make an assumption about essentially the spread of G and F on an element by element basis. Or such that. So let's say I know that the absolute value of G of X minus G of Y, right? So the distance between G of X and G of Y is always bounded by the distance between F of X and F of Y, okay, for all X, Y in the interval. So if this is true, then the G spread of I is bounded by the F spread of I. And this sounds like what should happen, right? You're taking the biggest things from G minus the biggest things, or the smallest things from G. That should be less than or equal then to the biggest from F minus the smallest from F, right? That seems reasonable. All right, but we'll make this precise. So we're going to actually be using the result from problem 6. Maybe that's not too surprising here. So we're going to do this in 2 steps. So first, if X and Y are an I, then of course G of X minus G of Y is bounded by the absolute value of G of X minus G of Y. But by what we have in the hypothesis, this is bounded by the absolute value of F of X minus F of Y. And now let's try to write down what this absolute value of F of X minus F of Y actually is, right? So if I wanted to compute this, I essentially am going to figure out which of these two, F of X and F of Y, is bigger and which is smaller. And I'll take the bigger one minus the smaller one. All right, because if I just did it directly, F of X minus F of Y, that might be negative, and the absolute value then would make it positive, which would mean I would really be computing F of Y minus F of X, right? So I'm just finding whichever one's bigger and subtracting whichever one's smaller. So I could write this as the max F of X, F of Y, minus the min of F of X, F of Y. Okay, but I'm looking at this for particular values in I, and the maximum of these 2 points, F of X and F of Y, is certainly less than or equal to the supremum of F on all of I. So if I replace this max with the supremum of F, right, on the entire interval I, that's certainly going to make this difference bigger. On the other hand, this minimum is bounded from below by the infimum of F on I, right? Every value I choose over here can't be any less than the infimum. So if I replace the minimum with the infimum, this difference gets even wider. So I can replace this here with the infimum of F of I. But the supremum minus the infimum is precisely the F spread of I. All right, so we've concluded that for all X and Y, the difference between G of X and G of Y is bounded from above by the F spread of I. And so what that tells you is that if I take this F spread of I, so this implies that the F spread of I, I'm going to write this backwards, in fact, the F spread of I is greater than or equal to, well, the supremum of all of the G of X's minus the G of Y's. So I could get the supremum of all differences, G of X minus G of Y, where X and Y are an I. Okay, so if you're greater than or equal to every term in the set, then you're at an upper bound for the set. And so you're at least as big as the supremum. However, in the previous problem, or the previous part of this theorem, I should say, we showed that exactly the supremum of this type of set is equal to the spread. So this supremum here is equal to the G spread of I. And so I've concluded that the G spread is less than or equal to the F spread. Okay, so we move on to number 8. And in number 8, we're just going to actually apply number 7 in a very particular case. Specifically, we're going to show that if I take the absolute value of f spread of, well, let's just say even a partition, that this is going to be less than or equal to the f spread of the same partition. Okay? So we're extending everything we did up above, actually now to partitions. All right, well, this really is going to follow again from the previous problem because we know that if I replace the f, or rather the g in the previous problem, with the absolute value of f, right, then let's see what happens. By the reverse triangle inequality, we have that the difference between the absolute values of f of x and f of y is less than or equal to the difference between f of x and f of y. All right, this is just an always true statement for any x, right, in the domain, right? So this would be true for all or x and y in the domain AB. Okay, and so this would tell me that on any interval, right? So thus applies if I is a subset of AB, then again by the previous problem, I would know that the absolute value of f spread on I is less than or equal to the f spread on I. Okay, and this is true for any I subset of AB, in particular when I write down all of my IKs corresponding to W. Okay, so this implies that the spread of f on IK is less than or equal to the f spread on IK for all k equals 1 to n. Okay, so here, just to remind you, right, we're treating our W as an n partition, and each ik is wk minus 1 to wk. Okay, but if this is true for all the individual pieces, well then what happens when I look at the spread of the entire partition, right? Well, remember, this is equal to the sum of the absolute value of f spreads on each ik times the length of ik. But now I can replace this spread here with the f spread, which is bigger. So this will be less than or equal to the sum from 1 to n of the f spreads of ik times the length of ik, and this is equal to the f spread of w. All right, so this is very nice. The spread of an absolute value is going to be bounded by the spread of the function. This will, again, be useful when we go to prove a certain integration property. Okay, we will see you next time when we finally jump in to those integration properties.